Hello everyone, I am Kanwar Pal Singh and I work as a product engineering architect with Cadence Design Systems. In my 20 years of career as a designer and later as an electronic design automation engineer, I have worked on various verification technologies ranging from simulation and then leading into formal. As part of Cadence, I am working on the JasperGold product and mainly driving the RTL static sign-off checks domain, which includes lint, DFT, CDC, and RDC checks. My co-presenter today is Bijitendra Mitra, who is also a product engineering architect working on JasperGold in the same domain as mine, and primarily driving the CDC and RDC checks. In today's session, we are going to talk about how you can significantly accelerate your sign-off by doing your RTL static check sign-off using JasperGold Designer apps. So this is our agenda for today. We'll start with the RTL sign-off by designers and talk about the big picture. And then we'll talk about, okay, how do you augment your sign-off with the auto-formal checks using JasperGold Superlint. And this will be followed by a quick demo of Superlint. Then we'll talk about functional and metastability aware verification using JasperGold CDC. And that will be followed by a small demo of the same. We'll conclude and we'll have a few minutes in the end for questions. So let's first look at the big picture. We all know that, we as much as we can shift left, that helps to, save cost and enables you to catch the issues very early in the design cycle. And it goes without saying, as if the bugs progress through the design cycle, the cost becomes high and the effort becomes high, and that is not good for any of the design. Okay, so if we look at the big picture now, typical RTL sign-off includes signing off your RTL against a comprehensive set of lint, DFT, CDC, and RDC checks. All the checks are automatic, and user just provides mainly the RTL and constraints when it comes to DFT and CDC, RDC checks. But all this is structural in nature mostly. So that's what we call here as automatic structural checks. For a comprehensive RTL sign-off, we believe that there needs to be augmented with some automatic functional checks. And what are these checks? These are high-value code reachability functional checks, those checks. And on the CDC side, this includes functional CDC and RDC checks, and also metastability aware verification. So we'll call this as automatic functional checks. And from a JasperGold point of view, if you see, JasperGold is uniquely positioned to give you a true integrated solution for combining the automatic structural checks and automatic functional checks under one integrated platform. And that is what will be the topic of our session today. And we'll explain you how you can augment your RTL sign-off with these additional checks leveraging formal techniques. And when we look at, okay, how are these automatic functional checks manifested? So these are mostly available as automatic formal checks, auto-formal checks as we call it, to augment the lint piece, and the functional CDC, RDC checks and metastability aware verification for the CDC, RDC piece as we discussed. Okay, so with that big picture in our mind, so let's go step by step and see how the auto-formal checks will help you in the comprehensive RTL sign-off. And it will appear that you are doing something additional as a checking, so it may take time. But if you look at the overall picture of this will accelerate your sign-off because you can now catch some of the high-value issues upfront without waiting for those to be caught later in your verification. So let's look at the auto-formal piece first. So why auto-formal? So the two keywords here, auto and formal, are important to understand why. So why auto? Because automation makes it easy for designers. Now here we are talking about the RTL sign-off by designers. So, we have to understand that we cannot be introducing a new thing here, which will require a lot of effort, extra effort by the designers. So the automation piece of this makes it easy for the designers. They don't need to write any properties. The properties can be extracted from the RTL, and most checks can be run without constraints. Some may require some constraints to reduce noise. And why formal? Formal is very exhaustive. That is one, and it does not require any test bench to begin. So that is the other part. So you can get started with formal much earlier than what you can do in the other verification techniques, where some development of test bench is required before you get started. So if you look at your design scenarios and along with the time vector, you can see that with the simulation it requires some effort to bring up the test bench, and then there's some lag till you get to the first bug which you catch, right? And secondly, simulation is all dependent on the test vectors, so you might miss some bugs which might be there in the design. On the other hand, if you look at formal, you can start much early, as I said, and your journey to the first bug would be faster, much faster. And formal being comprehensive, the probability of missing any issues will be lesser. So this will give you a significant shift left in your overall design sign-off and design checking and verification. So that's why we say that okay, let's augment your structural lint with the auto formal to actually help you sign off your RTL with much more confidence. So now we'll look at one example and see okay why auto formal checks are so valuable. Okay, so let's take this FSM example here. So this is a finite state machine going through various states, and one of the state here, if you see checksum, this exiting out of this state depends on this signal enq sop underscore id, right? So once the state enters this the finite state machine enters this state checksum, and this particular signal on which the exit depends, that doesn't go high, then checksum will be deadlocked. Now this is one scenario which you cannot catch structurally. The structural lint will not be able to catch such issues. And these can only be caught by automatic functional checks, which are, in our case, we are calling those auto formal checks. Now looking at the other side of it, the CDC, RDC side of it. The typical CDC, RDC verification has been structural as we started talking about it. And there has been a limited use of protocol checks and simulation with randomizable synchronizer model. So there is some augmentation with some protocol checks. And in the structural analysis, manual review is the key. And when it comes to manual review, given the number of crossings you might have in a large design, it is very tedious and error prone. And you end up generating a lot of waivers to get over and be able to sign off your design. And the verification is usually a disjoint step. It's not integrated into the overall static check sign off. So here also, why do we need the additional checks? So a lot of this verification happens with the CDC constraints, right? So there's a question: is my constraints which I have verified, are they correct? So you actually, to get a more comprehensive sign off, you need to analyze the correctness of your waivers. As I said, you end up creating a lot of waivers, right? So what about the validity of waivers? You made some assumptions about your design while creating some waivers. So you need to actually get the real sign off. You have to validate and make sure that your underlying assumptions which you did to create your waivers, they are correct. And thirdly, as I said, how do I guarantee that my design is immune to metastability effects? Is my functional verification correct in the metastability aware environment? So this is generally modeled with randomized synchronizer delay in simulation, which is pessimistic and incomplete. So you really require a more comprehensive approach to metastability aware verification. So now if you see, if you're missing these three aspects, you leave significant holes in your sign-off. So all this needs to be integrated into one flow, which will bring your structural analysis and functional verification into one integrated verification task, and then only you can really sign off your RTL with confidence. So with that background, where we looked at the big picture and we said that the traditional or typical sign-off, which only involves the structural checks, is not good enough, and you really need to augment that with the automatic functional checks, which are of two types, right? The auto-formal checks, which will augment your lint sign-off, and functional CDC, RDC checks plus metastability aware verification, which will augment your CDC sign-off. Let's look at these one by one, and I will be talking about the auto-formal piece of it, and then I will hand it over to Vijitendra to cover the CDC side of it. So now let's look at the the auto-formal checks in a little more detail. What are the types of checks and how they are integrated into Superlit with a short demo of the same. So we gave one example, we talked about one example of auto-formal checks in the earlier discussion. But if we elaborate on these checks, these are spread through various categories listed here, starting from the dead code, which will tell you about the reachability of the RTL code block, to X assignment, reachability of X assignment, FSM checks, which is not limited to only the reachability, but the live lock and deadlock checks on FSMs, signal checks, case checks, out-of-bound indexing, arithmetic overflow, and bus contention. And just a quick example of bus contention is that you have a signal which is multiply assigned, and if when A and B are both 1, you will have bus contention here. So you need to ensure that A and B are mutually exclusive, right? So these are all the categories of auto-formal checks. So coming to the tool side of it, JasperGold Superlint app is the app where all this is integrated into one. So we have the typical lint DFT checks, where we have hundreds of checks which allow you to do the structural lint DFT sign off. And to add to that, we have the auto-formal checks, which might require an additional configuration, not too much work, but some configuration in terms of clocks, resets, and some signal configuration. But that nicely fits into the overall story. And when you look at the view of it, in terms of what the user gets, he would get all these violations from all the different domains in one integrated tree. So that is how this makes the whole process much simpler and allows you to do all these checks in one integrated flow. And we already discussed in terms of input to this flow, we have the RTL and the Liberty models for the macros. There will be a rule configuration, which will, where you can specify which rules to run. And as I said, it's all of these three, lint, DFT, auto format. And once the run is complete, you analyze your results, you debug. So all that is one environment. And you create your waivers, you generate your reports, and based on your waivers and reports, you may need to also be iterating over the RTL to make some changes for the RTL before you can eventually sign it off. And in terms of the key productivity features for Superlint, there are a lot of features which help make this whole process much integrated and easy to use. But I'll talk about the ones listed here, where we have customized failure analysis, a persistent waivers, a grouping, observability enabled debug, and how you can leverage your formal to optimize structural lint results. And on the right hand side, we have just put 4 snapshots of the debug utilities available in terms of source code, FSM graph, schematic, and the waveform from the JasperGold visualize. Okay, so now let us look at each of these key productivity features quickly to understand how, in addition to a rich set of checks on the lint DFT side, plus a very comprehensive auto-formal checks portfolio, how these productivity features helps you to sign off your RTL in a significantly efficient way. So in terms of layout, we have two layouts. One is the violation layout, which is where you focus only on the violation without any consideration for the underlying properties for auto-formal checks. In this layout, you have the source code on the right side, and then you have the violation tree, which is one integrated violation tree, and violation from lint, DFT, auto-formal, all are shown in this tree. And then on the right bottom, you have the waiver list. So as you create waivers, they're all shown up here. And if you're really interested in the the properties which were created under the hood, you can look at the formal properties layout and the proof results if you're interested in those. In this, you have the source code here, like the violation layout. You have the task table, which shows you which the tasks were generated, and you also have the property table, where you will see the list of properties. The second productivity feature is persistent waiver. So this is a key feature here, because when you are looking at your RTL and analyzing your RTL, you don't want that, if you create a waiver, then next time the RTL changes, the waiver doesn't stick. So we really have persistent waivers mechanism in Superlint, such that the waivers which you create, once you right click a violation, you add a comment to create a waiver, and that waivers, gets listed in the waiver table below. And these waivers are persistent across the RTL changes, the file path changes, and even hierarchical. So the other key productivity feature is grouping, which enables a much more efficient analysis. What we do here is that all the checks which are similar, which is based on different heuristics, including similar root cause, they are grouped together, and there is a primary violation and there are secondary violations. So you can click on any of the violations which are grouped and see, okay, show me the related violations, and the related violations are shown accordingly. The concept around grouping is that if, in all probability, if you fix the primary violation, all the others which are linked to it as secondary violations will also get addressed. So if you see how this actually improves your analysis, because now instead of being presented with a flat list of violations which you have to navigate through, here you will have a much smaller list to look at. And to release the grouping, you can press on this button to release the filter. So the next thing here is more on the auto-formal debug side, which is observability enabled debug. So what we have here is that, whenever there is an auto-formal violation reported, you can actually debug and see whether this violation is actually going anywhere. I mean, when I say violation is going anywhere, I mean that a signal on which the violation, or the design node on which the violation is reported, is it going and impacting any further functionality in the design. And finally, in terms of productivity features, we have a very unique capability in Superlint where you can leverage format to optimize your lint results. So how this works, as we discussed, everything in Superlint is one integrated flow. So you have lint, structural DFT, and then the auto-formal checks. So there are some checks for which you have a check in lint and there is corresponding check in auto-formal. So the way this capability works is that if you have a lint violation and there's an auto-formal check, and the autoformal check also gets violated. So that means that violation has been proven to be happening in a automatic functional checks as well. So in that case, the lint violation is grouped under the autoformal violation. So that is how it is done. On the other hand, if the formal check is proven, that means the formal says that no, this violation is not happening because functionally it was checked and this path will not be traversed, or let's say this register is not impacting any output. In that case, the autoformal will be passing, and then what will happen is that it will optimize the result on the lint side such that the corresponding lint will be auto waived. So you will see the waiver list getting augmented with the lint violations which got auto waived because the corresponding autoformal violation passed.
Now let's quickly see a short demo of what we have discussed so far.
So hopefully you are seeing my Unix screen here. So what I have here is actually I did run the lint side of it. So I already have the violations showing here from the lint and DFT perspective. But just to quickly show you the underlying scripts. So my script is pretty simple. I just load a rule file, I analyze, elaborate, just do clock inferencing, and I do the superlint run. And the rule file I load is, there is, as I said, the whole thing nicely fits into one integrated flow. So you have all the lint categories. It's a subset I've selected here, some DFT. And then the autoformal also is part of the same rule file. So the autoformal property, categories are also here. And if I just scroll down, each category will have rules. And this is just a sample. And same is true for the autoformal side of it. Each category will have rules inside it. Same concept, same look and feel, but the power of formal is what makes these different and the high value. So what I'm going to just do and bring up the window back again. So what I've done so far is I ran the lint and DFT checks, and this is the result which you see from that. So what I'm going to do now is just switch to the formal. So this is my violation view of things. I'm just going to switch to the formal property layer to get the formal toolbar, and I'm going to run my formal checks on top of the lint and see the results. So I'm going to just press this button. There's a corresponding sickle command as well. So I just press this. So if you see here, the formal checks are running, and the results start populating in the same tree. So same look and feel, same debug capabilities, same reporting, same waiver capabilities, all fall in place here. So if you see here, now the autoformal part has finished. So my checks show up here. Before I look at little more of the autoformal, one capability we talked about was the leveraging of formal for reducing or refining the lint results. So this is my button. I'll just click this. So what you see here is this has done is that it waived some of my lint checks. If I look at the comment, it is saying that I waived this because of this particular corresponding check in the autoformal past. So that's why these got waived. So this reduces the number of checks I have to look at in the lint side now. The other thing which we have is that I talked about that we also group the related violations. If you look at the autoformal arithmetic overflow, and you pick up something. Let's say we pick this, and we say, okay, show me the grouped violations. I'll see that some of the group actually includes the lint. So that means the corresponding autoformal actually failed. So the lint got grouped, so that when I look at here, I'm actually looking at one violation. I can go and fix it. So the corresponding length and the autoformal both will get fixed. So that way, again, I reduce the number of things I have to look at. So this is a quick demo of how things work. So this is the GUI as I showed you, violation tree, the source code, the console, the waivers, and running autoformal is pretty easy. In the same setup, same rule file, you can just add those in and run it as part of your analysis, and then invoke the leveraging to get the benefit of the overall integrated run. Okay, so with this short demo, let me go back to the slides.
So to summarize, the JasperGold Superlint gives a rich set of checks which range from structural lint and DFT to including a rich set of autoformal checks which really help you to comprehensively sign off your RTL. And all this, is coupled with key productivity features which are enabled by the best-in-class debug platform based on JasperGold. And that is what enables you to really accelerate your sign-off and sign off your RTL with much more confidence. So from here, I will now hand it over to my colleague Vijitendra Mitra, who will take you through the rest of the workshop, where he will talk about the CDC side and how that should be augmented with the functional checks and metastability aware verification. Thank you, and over to you, Vijit.
Thanks, Kanwar. Now we are going to see how you can augment your current CDC RDC sign-off methodology with functional and metastability aware verification using JasperGold CDC, followed by a short demo. Just to recap on why functional CDC RDC checks and metastability aware verification is important, if we look at the major gaps that exist in the current CDC methodology, there are three things. First is the validity of constraints, which says that the analysis is happening under the right set of constraints. Second is the validity of waivers, which means the assumptions made during dispositioning of structural violations are valid. And the third thing is to guarantee that my design is immune to metastability effect. And to do that, my functional verification environment should be metastability aware. Now, all these three things can be achieved by functional verification, which means linking CDC-RDC analysis to functional verification is the key to complete and comprehensive CDC sign-off. Let's look at some examples to understand how these gaps can affect our CDC-RDC analysis process. In this example, we have an async FIFO, and the FIFO full signal crosses from CLK domain to the PCLK domain into a status register, which is essentially in the APB status interface. User did not bother to synchronize this path because it is going to a status register. Instead, he declared it as static so that the tool does not report any violation on this unsynchronized path. So far, so good. But in the next generation of the device, this signal is now used to generate some functional valid signals. However, the static constraint was not changed, which means that this wrong static constraint is now masking this valid functional issue of a glitch on the output of the flop because of presence of combo logic on the CDC crossing. If we had a way to validate the constraints, we could have easily caught this problem, which indicates that there is a missing verification linkage when it comes to validation of constraints. This is an example of a simple reset domain crossing happening here. There is a source flop and the destination flop. Both are in the same clock domain, but driven by different asynchronous resets. When RST1 is asserted and when RST2 is still deasserted, there is a possibility that the output of the source flop D2 can change very close to the active edge of CLK1 and which can cause the second flop to go metastable. Now, there are different strategies which are applied to avoid this kind of metastability scenarios in the design. Some of them try to gate the data crossing between the source and the destination flop, and in some cases, the clock to the destination flop is gated. But in all these kind of strategies, there is one underlying assumption that when the reset isolation logic is active, then the data path, the RDC path between the source and the destination flop cannot be sensitized. Now the question is that is this assumption valid? And at the same time, is the reset isolation logic verified in functional verification in context of RDC? It again points to a missing verification linkage when it comes to validating waiver-related assumptions. Now let's see what is missing in the current verification methodologies when it comes to metastability-aware verification. Typically, there would be randomizable synchronizer models that are used to introduce additional delay in the design, mimicking the metastable behavior. These structures would be using a flop to provide an extra cycle of delay, and this can be randomized. And as you can see that this one cycle delay is actually a pessimistic behavior which mimics the setup violation. But in case of hold violation, the output of the synchronizer can appear one cycle earlier than expected, which is not modeled here. At the same time, the synchronizer models are instantiated on paths where it can introduce the metastable behavior, but for paths where it is not instantiated, they never see a metastable behavior, although they are CDC crossings. Similarly, there is a lacking of metastability awareness in the verification process. So far, all the CDC tools have positioned metastability injection as a way to identify data coherency problems in reconvergent CDC structures. But if we look at the other design functionalities, there are several examples where metastability can cause a wrong behavior in the design. For example, if there is a clock gating logic which has its enable coming from a different clock domain through a synchronizer, or there are FSMs, state reachability and state transitions that can also get affected if there are signals which are controlling the transition are coming through synchronizers. Similarly, there can be wrong behavior in error correction logic, or even FIFOs can have performance issues if they have synchronizers in the fan-in, which can cause inordinate delays. So there are several other examples that exist where metastability can cause a problem in the design functionally. Now, which means that we have to re-verify the functionality of the design in presence of metastability to make sure that my design is immune to metastability effects. And all these can be done only if we have an accurate metastability modeling capability along with injection of that metastability behavior into the design. Let's look at what is true CDC RDC sign-off flow. The first two steps of any CDC analysis is CDC configuration and structural analysis. In CDC configuration, you would be defining the clock specifications, the reset specifications, and CDC constraints. And in the structural analysis step, there is a comprehensive set of CDC and reset checks which would be run, and on analysis, the user would also be generating a set of waivers. Now, till this point, it is a conventional CDC analysis or CDC methodology, and how we can augment this sign-off flow is to add functional analysis to it. Now, when we talk about functional analysis, as we have seen so far, there are CDC constraint validation, CDC protocol checks, and waiver condition validation, which are necessary. All the waivers that have been applied and the assumptions lying underneath must be verified in this step. Once the functional analysis is complete, Then we can move on to the metastability analysis step where we can verify either user written assertions or simulation test cases in presence of metastability. In addition, we can also validate the CDC protocol checks and the waiver conditions in presence of metastability to ensure that none of these functionalities break when metastability effect is injected into the system. Now let's see how you can achieve true CDC RDC sign-off with JasperGold CDC app. When we talk about augmenting the conventional CDC methodology with functional analysis, the first thing we do is to validate the constraints. JasperGold CDC is capable of automatically generating assertions to validate the constraints, and since it is proven in formal environment, it adds to a greater confidence. If the assertions fail, then the tool reports a violation and indicates that there is something wrong with the constraints. Some of these constraints can actually have a pseudo nature, which means only when a particular event happens, since then the signal becomes constant or static. Let's take an example. In this case, it's a simple CDC crossing between clock 1 and to clock 2. This is not synchronized because the assumption is that when D2 changes, then the destination domain is always under reset, which means that even if the user specifies D2 as static, there is a condition based on which D2 can be assumed as static. In JasperGold, you can specify this condition while declaring a signal as static, which would trigger additional verification of the pseudo nature of the static signal. You can also export all these signal configuration checks and run them in simulation. Essentially, you are verifying the constraints, which leads to a greater confidence on the quality of results you get from this CDC analysis. The other aspect of functional validation is to check for the CDC protocols. JasperGold tool is capable of auto-generating protocol checks for all identified synchronizers. At the same time, it also allows user to specify protocol checks for its custom synchronizers so that it can be replicated for every instance of those synchronizers. So far, CDC protocol checks have been mainly run with simulation because most of the tools did not have a strong formal capability. JasperGold comes in with its best-in-class formal engines, which gives you a much better proof coverage for the protocol checks. At the same time, you can also export these protocol checks and run them in simulation. This is a list of some of the protocol checks that the tool is capable of generating automatically. This is not an exhaustive list, but just to give you an idea about the kind of protocol checks that can be generated for specific synchronizer types. The third aspect of functional analysis is validation of waivers. There are two ways you can validate the waiver conditions. First is an auto waiver flow, where the tool automatically generates conditions for dispositioning the structural violations. If those conditions are proven to be true, the violations are waived automatically. Some examples could be grain-coded buses or even unsynchronized paths which the tool can prove to be metastability safe. The second option is the conditional waiver flow, where the user provides an expression as the waiver condition. If the tool is able to prove that condition, then it would automatically waive off a set of violations selected by the user. You can also export these waiver conditions and run them in simulation. What you are essentially doing here is to validate those waiver conditions and reduce the noise in structural analysis, and also to avoid any manual errors that may happen while dispositioning the structural violations. Looking at the metastability injection capabilities in formal, the prerequisite in this case is a formal property verification environment where user has assertions that are already passing. Now, JasperGold is the only tool in the industry today which would allow you to inject metastability and verify asynchronous logic in formal verification. It's a push button flow where the tool would automatically inject metastability into the design, and then you can verify the properties in presence of metastability. You can also enable the metastability awareness in protocol checks with this approach. The tool also allows you to do metastability injection in simulation. The prerequisite is to have a simulation environment with passing test cases. So it's a simple and easy to use flow which does not need any instantiation of any special modules into the design. JasperGold would generate some timing violation monitors and injection modules, and this can be exported to simulation. These injection modules are complete in nature that they can model both setup and hold violations, and they're not dependent on any synchronizer types. So all CDC crossings are covered when you are doing metastability injection in simulation. All these clocks have configurable setup and hold window, which would allow you to control the rate of injection. But at the same time, different injection modes are anyway supported, random being the default behavior. But for debug, you can always use the other modes like always injection and no injection modes. Coming back to the true CDC RDC sign-off flow with JasperGold CDC, what we have seen so far is that we can augment the conventional CDC methodology with additional steps when you run JasperGold CDC. In functional analysis, you can do signal configuration validation. You can do clock relationship checks, reset order or priority checks, CDC protocol checks, and waiver condition validation. In metastability analysis informal, we can do metastability aware proof of user specified assertions as well as the CDC protocol checks and the waiver conditions. When it goes to simulation, we can do metastability aware simulation on user test cases, and at the same time you can also export the CDC protocol checks, the signal configuration checks, and the waiver conditions and run them in simulation. If I look at the complete picture of how JasperGold CDC offers different capabilities and features, it comes with a comprehensive set of structural and functional checks, followed by metastability aware verification capabilities and innovative debug and waiver handling. This is the only tool in the industry which uses formal technology under the hood for functional analysis, asynchronous logic verification in form of metastability injection, and smart waiver handling. Now let's take a look at a short demo to understand how you can use JasperGold to perform functional checks and metastability aware verification to do effective CDC sign-off. I hope you are able to see my VNC. I already have the JasperGold CDC session up and running. I've run the structural analysis. And today in the demo, I'm going to show you three things. First, the constraint validation. Then I'll talk about waiver validation. And then we will see the metastability injection feature in simulation. But before I get into the details, let me walk you through this run file, which I've already run, and what are the steps that have been run so far. So first I load a custom rule file. You can choose to load the default one also, but I have loaded a custom rule file just to show you that you can customize the rules or the checks. Then I compile all the RTL. I load a liberty, and then I elaborate the design. I'm using an Ethernet MAC design here as my duty. Then I read the SDC, which has all my clock definitions, clock relationships, constant declarations, and the clock association for the ports. Then I have the reset declaration, and then comes the static declarations. And as you can notice, I mentioned during the slides that there is a condition specified for each of these static declarations, which says that only when this condition is true, the static property of this signal is valid. Then I have some false path declarations, and here I have the commands that actually run the structural analysis. There are different steps which we can run through for the structural analysis, CDC analysis, and then the structural reset analysis. Let me go back to the main window and show you the constraint validation. Before that, let me introduce the violation tree here. As you can see, there are two different domains, CDC and RDC, where we are seeing some of the violations being reported. As you can see under CDC synchronization, we have 3 no sync violation, which means that there are 3 scenarios where there is synchronizers missing. There are some convergence violations. As you can see here, there are some, let me just resize this. There are around 50 convergence violations, and there are some reset related violations, which are resetting data path. Now, if I take you to the signal configuration table, this is where you will see all the constraints that have been declared by the user. Here I have constant declarations, and if I scroll down to the bottom, you will see some static signals being declared. These are the ones which we saw in the tickle file. Now I'll just click a button which would prove these signal configurations are the static ones. As you can see, all of them have passed except just one. And because this one has failed, you'll see that one new violation has now been introduced in the violation tree, which says that this signal is not static. Now, if I go back to the tickle file, what it says is that this address 03, this is the one which is failing. The condition is that the reg CS second bit has to be 0 for this signal to be static. Now let's open the waveform and see what's going on. So I'll just do a debug violation. This will bring up the waveform. As you can see here, this reg CS signal is all along 0, but still this register has a value which is changing. Now I'll do a Y analysis on this. This is the feature in Visualize, which will bring up the source code browser. And as you can see here, this write signal is going high. That's why this value of 03 is being written to the register. Now, if I trace back on this write signal till I reach the reg CS, you will see that there is this reg CS 3 bit, which is actually a 4-bit signal, but the bit 3 or the fourth bit is actually going high. If I plot this, you will see it's the reg CS3, but not reg CS2. So I intentionally made a mistake in this static declaration to show you that if there is a problem with the static signal vis-a-vis its condition, then the tool would fail it. But there could be a problem in your RTL also that could have flouted this static behavior or the static property of the signal, and then also the tool would have reported a failure that the signal is not static. Now with that, we kind of verified all our signal configurations. Now I'll move on to show you the waiver validation, and in that I'll show you the auto waiver feature. So I'm taking you to the waiver table where we already have some auto waivers, but these are unconditional waivers based on some reset order. So what I'm going to do is I'm going to generate the waivers. Before that, I would try to point out that there are 3 no sync violations and there are 50 convergence violations. So based on whatever violations are reported, the tool is going to generate waivers. So as I run this command, you will see that several waivers are generated and all of them have a status of not processed. Now, I am going to prove these waivers, and based on the status of the proof, these violations would either be waived off or they would retain as violations. As you can see here, that some of these properties or waivers have already started changing status from not processed to safe, and you will see the number of violations are reducing. Since all these 3 are safe, So the no-sync violations are all gone. And if you see the convergence violations, it has reduced from 50 to 31. So this way, as you can see that once I run the auto waiver flow or do a waiver validation, so what happens is that I can actually reduce the number of violations in structural analysis. And at the same time, I can avoid any manual errors while dispositioning the violations during my review process. With that, I'll move on to the metastability demo. I already have a simulation session running. And as you can see, there is an assertion which has finished. And if I open the source browser, I'll just show you that this is an assertion, which is a data integrity assertion. I'm using the same Ethernet MAC design here. What it says is that there is a TX done signal, which goes high when the transaction is complete. The transmission, when it is done, we would check whether the number of bytes sent to the transmission module is the same as what has been transmitted out. If I look at the waveform, you will see that this is the TX done signal, and this is where it is sampled as high, and this is when the number of bytes sent to the transmission module and the number of bytes transmitted are same. So that's why the assertion is passing. Now what I'm going to do is run this same simulation in presence of metastability. So what I'm going to do is that I'm going to use this script where I'll show you. So there is a no MSI, which I've already run, which means there is no metastability injection. And then I'm going to run this section where I have included these files which have been generated by JasperGold. So all I'm going to do now is to run this MSI, which will run the simulation with metastability because I've included those files. And as the waveform comes up, you will notice that this assertion has now failed. As you can see, this assertion has failed. If I go back here, you will see that this is where the assertion has failed because the TX done signal goes high here, as you can see. And in the next cycle, it kind of does a comparison and it sees that the number of bytes are not same. Now, if I show you the schematic of the TX done signal, you will see that it actually comes through a synchronizer. The data 0 is the input to this flop, and data mid is the output of the first flop of the synchronizer. Now, if I look at these signals here, then you will see that data 0 is going high here at this time instant of 2423 nanoseconds. And there is a timing violation. So this is the injection witness I talked about. So it says that there has been a timing violation and it is of hold type. So that's why the output of the flop happens in the same cycle. As a result, the TX done actually is going high one cycle early, and which is kind of messing up with the comparison. That is why it is failing. So what we see here is there can be issues in the design which you cannot catch with regular simulation. So for that, you need such specialized capability of modeling metastability. And as you are seeing here that a hold violation has been modeled, but if you are using synchronizer models, so that can only model setup violations. So I'll just quickly show you that there has been a hold violation detected at this timestamp, and there has been a meta behavior, and the tool has injected a 1 instead of a 0. Now let's look at the takeaways from today's discussions. On the lint side, the RTL sign-off using typical structural lint is not comprehensive enough, and you need to augment your sign-off process with auto-formal checks, which you can do with JasperGold Superlint, which is an industry-leading solution for RTL sign-off, and it offers a comprehensive set of structural lint and DFT checks, high-value auto-formal checks, It's easy to set up and it is rich in analysis and debug features. And at the same time, it is designed to be low noise and a very high productivity application. On the CDC side, again, as we have seen, structural CDC RDC analysis is not comprehensive enough, and we need to link the CDC RDC analysis with verification to achieve true CDC RDC sign off. Towards this, JasperGold CDC offers you a holistic solution comprehensively comprising of structural checks, functional CDC RDC verification, which comprises of constraint validation, waiver validation, CDC protocol verification, and metastability aware verification in both formal and simulation. Thanks everyone for joining this session and listening to us. Now it's time to take some questions.